Hello everyone. First of all, let me thank again the organizers for giving me this opportunity to talk to you about exact formula for Wigner functions at equilibrium. This presentation is based on two papers, one already available on the archive, plus one work in progress. And both of the papers are in collaboration with Francesco Beccattini and Matteo Buzzegoli. Now, I'm really, let's say, excited about this talk because just to give you a preview of the results, here for the first time, I will present an exact results at for mean values and expression at equilibrium with both acceleration and rotation in the case of global equilibrium. So this expression here is, for instance, the, say, key result of the presentation, and is the exact Wigner function for fermions at general global equilibrium, so including effects of acceleration and rotation again. And it is the first time one such function is shown. Now, we are interested in computing exact mean values and exact solutions in this kind of equilibrium because they will give us the full quantum corrections so as to apply them at hydrodynamic of relativistic fluids. And the presentation will focus on answering the question of how to compute them, how to compute exact mean values. Now, in order to answer this question, you will find throughout the presentation 3 blue boxes, just like this one, where, say, the key ideas are contained. So understanding these 3 key ideas will allow us to answer the question. Now, very briefly, an outline of the presentation. First of all, I will start by briefly recalling some notions of thermal equilibrium in quantum relativistic systems. Then I will talk about field theories and Wigner functions. And in the end, finally, we will tackle the problem of exact mean values, and I will show the newly developed technique to compute them. So without further ado, let me start just by recalling that a quantum system can be described by a density operator, ρ, and this density operator is then used to compute mean values by computing the trace over the full Hilbert space of the quantum system. Now, the more general equilibrium in special relativity, neglecting chemical potentials, is described by this operator I have written in the slide, where zeta is the partition function, b mu and omega mu nu are constant parameters, and p mu and j mu nu are the generators of translations and Lorentz transformations, respectively. So we will be dealing during this presentation with a density operator, which is actually an exponential of the generators of the Poincare group. And this observation will be important later on. Now, in this kind of systems, the temperature is, of course, a vector, which is generally directed along the velocity, and T is the comoving temperature, which is, of course, which can be found by computing the square of the fourth temperature. However, at global equilibrium, this fourth temperature has a, say, simplified expression and depends on the parameters of the density operator, and is a killing vector of in the Minkowski spacetime. Now, this omega is an antisymmetric tensor. It is called generally the thermal vorticity. And we can make a decomposition, a completely general decomposition in a similar way as we can do with, say, the F mu nu tensor of electromagnetism. So we have a magnetic part, this W rho, which at global equilibrium is related to the rotation of the angular velocity of the fluid, which is this omega, and then the electric part, which is related to the acceleration of the fluid. And that's why we call this kind of equilibrium with rotation and acceleration. Now, as I said, we want to compute expectation values in field theories with an equilibrium described by this very general density operator. This task is made very difficult by the presence of the boost angular momentum operator. There are techniques to compute mean values in this kind of system, but only in the case of pure acceleration or pure rotation, never the two together at the same time. And these techniques always rely on the solution of the field equation in a particular set of curvilinear coordinates. Now, we do not want to use this method. We want to use a completely different method, which exploit the similarity of the density operator with the Poincare transformation. So without solving equations in any kind of curvilinear coordinates, we will always be in a Minkowski spacetime. And that brings us to the first key idea, which is to fully exploit this similarity. We can analytically continue the thermodynamic parameters to imaginary values and then factorize the density operator, so to deal with a translation and a Lorentz transformation. Explicitly, this is done as follows. You can map the thermal vorticity into this purely imaginary tensor. And then after this mapping, you can use Bacher-Campbell-Hausdorff formula and factorize the density operator like this. Now, the second term is just an ordinary Lorentz transformation with some angle phi. And the first term is instead a complex translation of a vector tilde b. This tilde transformation is defined in the slide, and it depends on the tensor phi. And this dependence takes into account the fact that p mu and j mu nu do not commute with each other, because of course the Poincare group is non-abelian. Okay, so now that we have this factorized expression, we can deal with a density operator which is actually a Poincare transformation. And this will be very useful because we can now use group theory to compute mean values. So very, very nice, let's say. And on the other hand, we always have to keep in mind that the operator continued like this is describes an unphysical situation. And for example, you can readily find out that this operator is no more Hermitian, whereas a density operator must be Hermitian. So, however, we can still use group theory to compute mean values, but at the end of our calculations, we have to continue our result back to real vorticity, to real thermal vorticity, to obtain physically meaningful quantities. Okay, so far so good. Now, let me move to field theory. During this presentation, I will always consider fields as free, so no interaction, no magnetic fields, and so on. And I will focus on to the scalar and the Dirac field in Minkowski spacetime. Here I have written the expansion of those fields in normal modes. And you can also recognize the presence of the creation and destruction operator, which are normalized so that the commutator or anticommutator is covariant. So it's given by this expression where epsilon is the energy. Now, as we have seen also in the previous talk, in order to compute mean values in a field theory, it is very useful to introduce a Wigner function. So here you can read the definition of the Wigner functions for the scalar and the Dirac field. And we can compute mean values in our field theory by making integrals in the variable k of these Wigner functions. Also, with each Wigner function goes a Wigner equation. Here you can read both the Wigner equation for the scalar field and the Dirac field. And here I have restored h bar just to mention again that this equation are used to compute, say, perturbatively the semi-classical expansion of the Wigner functions. Now we have simplified the problem of computing a mean value in a field theory to the problem of computing a Wigner function. We can again simplify the problem because if we plug the expansion of the fields in normal modes into these definitions, we realize that the building block of any mean value is given by the mean value of a number operator. Now, to compute this mean value, we can use our complex density operator, say, and we can use group theory now. So we Lorentz transform the creation operator, then we act with this translation. And after using also the commutation and or anti-commutation rules for these operators, we obtain this equation. Okay, some remarks about this equation. First of all, let me mention that this equation holds for any spin or helicity S. So it holds both for massive and for massless particles. And we have also these matrices W are generated when, appear when Lorentz transforming the density, the creation operator, and are well known in group theory. Here you can read their definition, where with this square bracket of P, I mean the Lorentz transformation from the rest frame of the particle to the frame where it has momentum P. And in the case of massive particles, these transformations are rotation, so and are called Wigner rotation. So here in this equation also appear this particular rotation related to the Lorentz transformation of the density operator. Also, it is important to notice that in the case of vanishing vorticity, this equation reduces to the usual algebraic equation, which has as solutions the Bose-Einstein and the Fermi-Dirac distributions. Now we have to solve this equation, of course, for non-vanishing vorticity. And to do this, we arrive at our second key idea. To do this, we can try and proceed iteratively. So by that, I mean this. As a first step, you can approximate the mean value of the number operator with only the last term of the previous equation, so the term involving the delta function. Then you can compute an updated version by looking at what this ansatz would produce in the equation, again, in this term here. So if you continue updating your expression infinite many times, say, finally you will end up with a series, which again is a series which holds for any spin or helicity. It is a very peculiar series, of course, because it is a series of delta functions. But again, if you compute the series in the case of vanishing vorticity, you will obtain Bose-Einstein or Fermi-Dirac distribution according to if the spin is integer or half integer. So what this series represents is the exact mean number operator in the case of equilibrium with non-vanishing vorticity. But however, we have still to continue our expression to real thermal vorticity. Now, before doing that, however, we can use our building block to compute a Wigner function. And now we arrive to the very first formula you have seen in my presentation. This formula here represents the exact Wigner function for equilibrium, global equilibrium with rotation and acceleration. You can see again that this is a series of delta functions. It depends on the tilde transformed temperature, and it involves these matrices, which are just Lorentz transformations in the representation of the Dirac field, because this sigma is the commutator between two gamma matrices. Whoops, sorry. Okay, so this series again is peculiar because of the presence of the delta function, but if we are to compute a mean value, we will have to integrate over k. So the delta function will disappear, and we will be dealing with an ordinary series of functions. Also very important to mention that this expression we can check explicitly that fulfills the Wigner equation for imaginary thermal vorticity. So it is a reasonable Wigner function and an exact solution to the Wigner equation. And if we say restore again h bar in this exponential, we can compute say this full semi-classical expansion in H bar. I'm sorry, Giorgio Torrieri, I heard your remark earlier. Okay, so that now that we have a Wigner function, and that we can of course do the same in the case of the scalar field, we can try and compute some mean values. So, for example, let's try and compute the mean stress energy tensor in the case of pure acceleration. This decomposition is general and it is constrained by symmetries. So we have the stress energy tensor, here rho is the energy density, P is the pressure, and A is an anisotropic term for the pressure along the acceleration. As I promised, the mean stress energy tensor can be given by some integrals in K of the Wigner function. Here I have written the canonical stress energy tensor. And so after this integration, the delta function disappears, and we end up with ordinary series of functions. And for instance, we can say try and compute the energy density. According to our expression in the massless case, the energy density is given by this series, which depends on the unphysical parameter phi. Now we want to make this mapping back to the physical acceleration, because the physical parameter is the acceleration, not phi. However, if we try and make this mapping at this stage, a catastrophe happens because the series becomes badly divergent, because it becomes the series of 1 over sine. So there is a problem, and we have to understand where this problem stems from. To do that, we have to make some steps back to the equation for the number operator. In the scalar case, the equation reduces to this one, so no Wigner rotation. And in general, a similar equation has a structure of solution very similar to the solutions of a differential equation. We have a particular solution, S0, which is actually what we have found via our iterative method, plus this H is the solution to the homogeneous equation, which is highlighted here in gray. Now, if we want to study deeply this equation, we can try and, for instance, study the solutions of the homogeneous equation. And now, studying these solutions, we find out the source of the problem, because it can be shown that if a non-trivial solution exists to the homogeneous equation, then this solution is a non-analytic function at phi equal to 0. And that's the origin of the problem. An example where one can explicitly find a solution to the homogeneous equation is a scalar case accelerated with acceleration, say, along the zeta axis. And this family of solution solves the homogeneous equation, and you can recognize that they are not analytic in phi equal to 0. So that's our problem. We have in our solution, we are accounting for unwanted non-analytical solutions. And to solve the problem of the convergence of the series, we have to introduce some mathematical operator so to remove these non-analytical solutions and only to retain the analytic part of our series. And this is just the third and last key idea of the presentation. And this operation has been called analytic distillation. And let me just sketch to you how this operation works. Suppose you have some complex function, which you can think of as the combination of an analytic part and a non-analytic part. So you can think about this like, say, a solution of water and salt, say. Now, to single out only the analytic part, you can use as a tool an asymptotic power expansion. So if this expansion exists and it is a convergent series, this is very important, then what you have actually obtained is the asymptotic expansion of the analytic part of the complex function. And so after computing this asymptotic series, you have successfully singled out the analytic part of your complex function. More formally, and this is the definition, you can suppose you have a function which can be maybe not analytic in some point zeta0 of the complex plane. And suppose a power expansion exists with powers also with negative powers, for instance. Now, it can happen that the coefficients of a fixed degree in power series of the expansion, it can happen that they are different in different subsectors of the complex plane. This is an occurrence which is well known in the theory of asymptotic expansion, and it is called the Stokes phenomenon. If this happens, this is just a signature of some non-analytic behavior, and our description, our prescription for the analytic distillate is to just remove those coefficients, so put them to 0, and only retain the coefficients which are globally defined into the whole domain you are considering, and to retain only the positive n in the expansion. So if the series obtained like this is convergent, you call the series the analytic distillate at the point delta 0 of the original function. And here I have written the definition with this capital A, which are the coefficients globally defined into the whole domain. So in some sense, this is a procedure to single out the analytic part of some function. So in some sense, it can be thought of as, say, the inverse of the resurgence phenomenon, if you're familiar with that. Now that we have this new tool, say, let's try and head back to our example and compute the mean values. Let's see if now everything works fine. So the series for the density, the pressure, and the A coefficients are given by this series. All of these series suffer from the same problem, because if you map phi into I times A, I times the acceleration, all these series diverge. However, if we compute the distillation, we can use a very useful theorem by Zagier to compute the full asymptotic expansion of the whole series here. And we find out that the full asymptotic expansion is just some polynomial. So we have these three polynomials, and what we have done is that exactly we have singled out the analytic part. The difference between this series and this polynomial is just a function which is not analytic at phi equal to 0. Now that we have analytic functions, we can finally continue our result back to real thermal vorticity. And we obtain these results here. Now, these results, we have also checked that computing the stress energy tensor in Rindler coordinates, we can recover these exact same results. And these results also agree with the previous literature, in particular with this paper by the next speaker, Georgi Prokhorov, which however found these results perturbatively. Now, also a very important thing to stress out is that these expressions automatically vanish at the Unruh temperature, so are in full agreement with the Unruh effect without any these are just this happens automatically without considering the difference between vacuum of the field theory. Also, we can compute mean values at equilibrium with rotation. This kind of equilibrium is somewhat more technical and much harder to interpret also physically. However, our procedure again exactly reproduces the results known in the literature, in particular in this paper by Ambrose. And the same also applies in the case of fermions. For instance, for massive fermions, we have these expressions for rho, p, and a. And again, these expressions automatically vanish at the Unruh temperature. In the case of equilibrium with rotation, we can also compute the exact axial current for massless fermions, and we find this expression, which again is in full agreement with the previous literature. So this new method reproduces exactly what is already known in the literature, but actually we can do something more because we have the exact Wigner function at global equilibrium with rotation and acceleration. So we can try and compute the exact spin density matrix and the exact polarization in this particular kind of equilibrium, actually a very general kind of equilibrium. So the spin density matrix is defined like this, and is a matrix which contains, say, all informations concerning or thermodynamic information concerning spin, and it can be expressed using the Wigner function here of the Dirac field with this expression here. Now, if we plug our exact Wigner function into this expression, we can do some calculation and we end up with this expression for the numerator, just the numerator of the spin density matrix. The denominator is just the trace of this expression. And I mean, this is some hard, it's somewhat difficult to read. However, we can use this expression to compute the exact spin polarization vector, which is given by this formula, where again you can recognize square bracket of k as the boost, as the transformation from the rest frame to the frame with momentum k. And here are the generators of rotations in some spin S representation of the rotation group. If we plug the density matrix in the previous slide into this equation, we can compute the spin polarization vector. And indeed, we can check that at up to first order invorticity, we obtain a formula which again exactly matches the literature. In particular, we obtain these results, with this result, which already have been quoted many times during this workshop. However, our solution for the spin density matrix contains all orders in vorticity. So we could find the spin polarization up to all orders in vorticity. So very, very nice. Now we are arriving to my conclusions, to the end of the talk. And first I would like to make an outlook, a little outlook. So here we have tested this new method, always comparing with something which can be computed also in curvilinear coordinates. And we always found agreement. However, the method introduced has the advantage that can be used also for general global equilibrium with both acceleration and rotation. So it can produce the first exact mean values and exact expectation values for equilibrium with both acceleration and rotation. Also, we have calculated the exact results in the massless case using the technique of analytic distillation, but this technique can also be generalized to also applies, say, to the massive case. So we could also compute exact mean values in the massive case. And now, just to conclude, I want to wrap up what we have done. We have determined the exact solution at general global equilibrium with rotation and acceleration. And we have introduced a new mathematical operation on complex function. And this operation, the analytic distillation, allows us to extract the analytic part out of a potentially non-analytic function. And using the techniques proposed in this in our works, we could derive the expression of the spin density matrix and the spin polarization to all order of thermal vorticity. So with this, I conclude, and thank you for the attention.
Yeah, thank you, Andrea, for being precisely on time. And so now so now the session is open for questions. So let me start. So I see some raised hand. Let's start with Dirk. Yeah, Andrea, thank you for the nice talk.
Thank you.
I just would like to understand better this result where you compute the Wigner function, including this parameter lambda, or was it the Lorentz
Yes.
transformation? What do you do exactly there? I mean, lambda is that's the rapidity, or is it the parameter for the Lorentz transformation, or
In this expression, lambda is a Lorentz transformation. It's
the
just a Lorentz
matrix?
transformation. So the parameter phi is this analytically continued thermal vorticity.
Okay, and the lambda depends on.
Lambda is just is defined with just like this one, but with generators in the four vector representation.
Vector
So it's the
representation.
exponential of phi times.
Okay,
3.
very good. Okay, yeah, thank you. That was one question.
Okay.
Next question is by Kenji.
Yes. So, your talk is super interesting. I'm very much interested.
Thank you.
So my question is about analytic distillation. So you slightly mentioned the resurgence theory, and I know what resurgence theory is. That is just the absence of pause to avoid the ambiguity. So, but it seems that you dropped some dangerous terms. And so I want to see some relation between your manipulation and resurgence theory. So could you please explain?
Yes, actually, I am not at all an expert on this topic, but I found it very interesting. And this is just the very first definition we have given to this operation. We would like in the future to expand this operation of distillation in terms of trans-series and resurgent theory. Unfortunately, at the present time, I cannot give a better expansion on how this is related to resurgence, but we think there is a link.
Your conjecture, yes, it's your
yes,
conjecture.
Yes, it's a conjecture.
Okay.
It's a conjecture.
Yeah, but it's really likely that there is an interesting relation.
Yeah, I think so. Thank you.
Maybe I can comment about this.
Oh, please.
For Kenji. So far, this is just some conjecture, as Andrea said. So we cannot say that this is an inverse operation of resurgence, but it looks like that in resurgence, what you want to find is non-analytic corrections to the perturbative series, right? And
yes, but in the resurgence theory, the point is that when you have such dangerous series, then you can do the Borel summation. But the problem is there is ambiguity in the inverse Borel transformation. But that ambiguity is automatically cancelled out. That is the point.
Yes.
Okay. So let me suggest then to postpone this discussion to the roundtable. So this is interesting, but let us postpone it. So let's now go to the next question by Lin Shu.
Okay. Can you hear me?
Yes. Hi.
Oh, okay. It was a very nice talk. So I want to have a question on the setting. So you have both acceleration and the vorticity, and it is in global equilibrium. So I was wondering, I mean, for fields with constant acceleration, would it cause a causal behavior? I mean,
a causal behavior. Actually, there are problems with causality at equilibrium with rotation. Acceleration has there are no problems there. Actually, there are some problems at equilibrium with rotation, very technical problems, however, because this operator becomes not bounded from below, and you can have some regions where unphysical solutions appear, say. So, and you can violate causality. However, this is a very technical issue, which is not solved. And yeah, is that.
Yeah,
however, these solutions with acceleration have no problem at all with causality. Where are they?
But if you wait for long enough time, wouldn't it exceed speed of light?
No.
Okay. What I have in mind is analogy analogy between electric magnetic field and acceleration and vorticity. I mean, there people have killing conditions that to use gradient of chemical potential to exactly balance electric field. So you don't have similar mechanism here for the acceleration, right?
No, because we are considering only a free theory, only free theories. No.
Sorry, there is. I think that. Sorry, Andrea. I think there is. The question by him is equilibrium. So if you have a killing, say, if you have a killing equation, and it is.
I mean, the killing equation. Of course, this is.
This is understood.
As I mentioned, this is a killing vector in. Without magnetic fields, and so this is a general killing vector in Minkowski spacetime. So any killing condition is fulfilled.
Oh, okay. Thanks.
Okay, no, sorry, I didn't understand. Okay.
So I would like to ask now Victor Ambrus to speak, as he was involved in a sense.
Hello. Hi, Andrea.
Hi.
Thanks for a very nice talk.
Thank you.
I just want to mention one problem. Okay, not one problem, just one idea, which has plagued, let's say, the analysis of boson fields in rigid rotation. So this, let's say, this plague dates back to the days when people were looking at thermal equilibrium states around black holes, especially around rotating black holes. So the idea is the following. One can easily imagine that the Bose-Einstein distribution exhibits some kind of a pole when the energy of the bosonic quanta vanishes. Okay. So in a rotating equilibrium, what is interesting is a corrotating energy, which is more or less related to the corrotating rigidly corrotating frame. In this case, you would end up with a distribution which vanishes not at zero Minkowski energy of the quanta, but at zero corrotating energy. So immediately, mode sum calculation of rigidly rotating states for bosonic fields will be divergent everywhere. But the perturbative calculations that Professor Beccatini and his group, and including yourself, employ, give some finite values, some finite results, which can be expressed as power series with respect to the vorticity. So I was just wondering if there is maybe hidden in this analytic distillation also a solution to this divergence problem, because the divergence problem has a completely, let's say, different origin.
Actually, I don't know. Maybe, but it can be. However, this analytic distillation, actually, I'm thinking it can be because with this distillation we single out some non-diverging part of the results. But unfortunately I'm not familiar with this problem, so I cannot give you say an answer, a sure answer to this question. I'm sorry about that.
I think it's a very old question, and yet the answer, whether the thermal rigidly rotating state exists or not for bosonic fields, is unanswered, in my opinion.
Yeah, I think so. Maybe using this technique, one could have some more insights, but I don't know. I don't know.
Okay. I think this is also a very interesting discussion to continue in the round table. Certainly, I'm also interested in that. Now we have two more questions. One by Masoud.
Thank you, Andrea. Thanks.
Hi.
Thanks for the nice talk. I actually wanted to ask about the same question about resurgence, but now I'm making a comment. Actually, by brute force, I mean, we were working on the hydrodynamic solutions, And we saw that it can be, you can find a convergent solution to the hydrodynamics in certain setups. And I think now that this is exactly what you're talking about. We couldn't understand that at the moment.
Sorry,
but
can you
I
be
think this is,
can you be more precise? What do you mean by convergent solutions for hydrodynamics?
For example, if you solve the Birken in the MIS formalism, for example, okay, you will end up with something that if you want to, if you will end up with a divergence series that you need this resurgence theory to put the dangerous parts.
Okay.
I mean, handle the intelligence part in some way, okay, and is an analytical structure of the Borel summed series. But it seems that if you stop at some pole, when you end up with the convergent series, yes, and that solution, yes, is a very good approximation. At times goes on, and it actually gives you a precise value for the hydrodynamization type. But this was all done by brute force. You know, we just tested if that works, and we saw that it works. But it seems that this analytical distillation is actually the basis of such thing. Yeah.
Yes, yes, it can be. As you have said, you were dealing with resurgent theories, so
I can share that if you.
So if our conjecture about the link with resurgence is true, yes, I think it's exactly the same situation. I think so. Yeah. We have some non-analytic term which cause divergence, and we have to handle them out in some way. So a very similar situation indeed.
Yeah. Very good. So there was one last question by, I guess, by Oleg, and then by me. Just it was my mistake that I have clicked on the raised hand. So Oleg, can you ask your question?
Well, just thanks just for interesting talk, and I have a related question on the physics beyond behind analytic distillation. I would suspect that it may be considered as a sort of renormalization. Actually, it's a bit similar to minimal subtractions in field theory, when the poles in epsilon, which is deviation of dimension from 4, are just dropped. Mm-hmm. And just, would you consider this really a sort of renormalization affecting the physical result? And maybe, by the way, dropping some essential terms, as it was just discussed. And well, and what are, if you have a renormalization, there are, it should be the, what is called physical conditions of such renormalization.
Yeah.
It's not always easy to find this physical condition like in Casimir problem, but so would you agree that it is a renormalization affecting the physical result? And do you have ideas about physical conditions?
I mean,
such renormalization?
Okay, so because of the absence, as you said, of physical conditions to renormalize the theory, I am in some sort of doubt if I would call this renormalization. I would call this rather maybe regularization. So it's a way to remove some divergent contribution that is unphysical, at least for what we understood.
Usually regularization is considered to be some temporal removal. So after that, after regularization, it's the parameter of regularization should be go to 0 or to infinity. But if you make regularization and drop something, this is like minimal subtraction. You make dimensional regularization and you just throw away the poles. Here only poles are non-analytical.
Yeah, this is in this sense is similar. However, there are no scales, so there is no Kalan-Simanzik equation and so on. So I don't know. I mean, there are, for sure, there are some similarities, but I don't know if I would call this a renormalization. However, there are some similarities indeed. Thank you for the questions.
Okay, thank you.